Alright guys, here I am. I'm going to try to do this practice test as fast as possible, so hold on to your calculators. We've got to find the absolute max and absolute min over that closed interval from -1 to +3, so just pay attention to that. I'm going to find the derivative. This should be a piece of cake for you veteran derivers. 4x to the third minus then 12 with the power rule x squared plus 8x and then plus 0. I'm going to set this equal to 0, but before I do that I'm going to cancel a 4 everywhere. That's just common sense. And then I'm going to factor out an x. So just cross out the 4 and get a 3, cross out the 8 and get a 2, and then take out an x, and then I get x squared minus 3x and then plus 2. Well, I can factor that then pretty simply. I hope this is an easy layup for you guys. X minus 2 and x minus 1. You can always use quad form on your calculator if your factoring skills have gotten rusty. So I get critical points at 0, at 2, and at 1. Okay, so now I'd pop it on the calculator, and I've taken the time to do that in advance. When I go to my graph, I get something that looks like that. I've done a zoom box around the interesting bits. I've gone from about -1 to 3. You can also go to your window and go from like a little bit more than -1 to a little bit more than 3. Then what I like about this is if I do trace, I can then just enter my key values. So I'm going to put in f of -1 for the first endpoint, f of 0 for my critical point there, f of 1 for my next critical point, and then f of 2 for my third critical point, and then finally f of 3. Okay, and I'm going to see where my absolute max and mins are when I put those in. So -1, enter, I get positive 14. When I plug in 0, hit enter, I get 5. When I plug in 1, I get 6. 2, I get 5 again, and 3, I get 14. Okay, so a bit of a strange problem in that I have two absolute maximums. I have 14 and 14 at both endpoints, and then I have two minimums. I guess I'll maybe put the max there and the max there, and that's a minimum. Alright, now don't let that bother you. Then 6 would be a relative or local max. Alright, there you go. On to the next problem. I should sketch that in and just label it. I don't have time to do that now. I do have time to write answer key. Okay. These next three are L'Hopital's rule. That will help us with limits. Limits when you get problems like 0 over 0, or infinity over infinity, or infinity times 0. All right, these are really the two cases we are concerned with, and we'll deal with this later. When this is 2, I can't just plug in 2 because I get 0 over 0. So that's an indeterminate form. That is what L'Hopital's rule is designed to solve. I take the derivative of the top, and I get 3x squared over then 1 when I take that derivative. So I get the limit now as x approaches 2. Well, I can just plug in 2, and I'm going to get 12 over 1, which equals 12. So that is my limit. It approaches 12. This one here, again, if I plug in 1, I get e to the 1 minus 1, which is 0. E to the 0 is 1. 1 minus 1 is 0. And then if I plug in 1, I get 1 minus 1. So this again is 0 over 0. So I do smack it with L'Hopital's rule, and the derivative then, d dx, just to rewrite it, of 1 minus e to the 1 minus x. Well, when I take the derivative of this, I take the derivative of the first thing, that's 0. Now the derivative of negative e to the 1 minus x is just itself, minus e to the 1 minus x. Then I take the derivative of the inside. This is a chain rule. Well, the derivative of that is minus 1. That is just then e to the 1 minus x. Okay, that's the numerator. The denominator, do not, repeat, do not do a quotient rule. Take a separate denominator of each of those. Well, the derivative of the denominator is just 1. Alright, well I have this now, and I can sub in 1, and I get e to the 1 minus 1, which gives me e to the 0 over 1, which gives me 1 over 1, which is 1. Okay, so that is that limit there. Now this one is not in either of these first two forms. It's in this third form. This I'm going to do a clever little bit of algebra to reduce that to L'Hopital's rule form. So I have the limit, and I'm going to write as x goes to 0 e to the 1 over x, but then I'm going to take this x right here and I'm going to multiply this by the fraction 1 over x over 1 over x. Okay, so this is just over an invisible 1. What I'm really trying to do is get this down into a denominator. And I do that by multiplying by something that will cancel with it. So I haven't just made that up out of thin air. I know that 1 over x will cancel with x. So they're gone. And then this becomes the limit as x approaches 0 of e to the 1 over x over 1 over x. Well, when I plug in 0, these are both going to infinity. So it's an infinity over infinity style. When I take the derivative of the top and the bottom, I should be able to make sense of it. So the derivative of the top is just going to be e to the 1 over x times the derivative of the inside. Well, the derivative d dx of x to the minus 1 is just negative x to the minus 2. So that's going to be times x to the minus 2. That's the numerator. And then the derivative of x to the minus 1, as we just found out, is x to the minus 2. Well, these cancel, and then this is just e to the 1 over x. As x gets closer and closer and closer to 0, that just blows up to infinity. E to the infinity is infinity. Oh, I didn't write that very well, but that is e to the infinity. Let me write that again. I'm trying to write so that the camera shows it. Okay, that's the first page. Okay, here we are at the start of the second page. I filmed a little bit, then I made a mistake and accidentally deleted it. But we've got this container that has corner cutouts. Sometimes that's hard for kids to see, but this is just a square cutout that's going to be x by x. If you cut out the corners and then fold up the sides, that height right there is going to be x tall. The width right here is going to be 20 minus x at both corners. So we get here 20 minus 2x is the width, 30 minus 2x is the length, and the height there is just that cutout height x. So you get this. You can FOIL it all out, but I actually, just for variety, I didn't. I just brought the x inside, and then I've got two things multiplied, and I just, for practice, did the product rule. So I took the first times the derivative of the second, that's that, plus the second times the derivative of the first, that's that, and I get this is the derivative formula right there. Now, I actually think that's a little bit harder, so I invite you guys to simply do the foiling, and then you can very simply take the derivative and you get that. Once you're at that, you can pop it into quad form on your calculator, or you can factor out a 4 and then put that into quad form. Okay, thanks. Okay, I'm back. The calculator I had did not have quad form on it. I actually did an old school method, but once you get the derivative here, and you can just, if you have the quad form on your calculator, you could put in 12, negative 200, and 600 for c. If you factor out the 4, you then can write it in a little more simple form with a equals 3, b equals negative 50, and c equals 150. When you do the quadratic formula longhand or quad format on your calculator, you're going to get two answers. One is that its x is 3.925, x equals 3.925, and the other is that x is around 12. Well, there's no way you can cut out a corner that goes more than halfway, so that's a ridiculous answer. So this turns out to be the best dimension for that. Now, just so that you know, you can always check your answer on a calculator by going to y equals, and I just typed in the basic formula. I didn't even FOIL it out. I went to my window and I made my cutout go from 0 to 10. That's halfway to 20. And then I just made my volume big, and you can experiment. If you guess too small, you can make it bigger. And then I do get a graph that's like this, and by doing second trace I can find the maximum value, and sure enough that maximum value for the volume does happen at 3.925. Okay, so now we've got two cars that are speeding towards an intersection, and we want to find the rate of change of the distance between the two cars. So a good picture is always helpful. So one car is heading south, and that's in the y direction, and that's at 60 miles per hour. And it's worth noting the units, all right? That's miles per hour. And the other car is heading towards that same intersection that's like right there, and they're both 1/4 of a mile away. So they're both 1/4 of our unit miles away, and this one's going at 45 miles per hour. So what is this distance between them changing? I'm going to call that L, and this is my x direction. That's my y direction. So my basic Pythagorean rule applies: x squared plus y squared equals L squared. These are all three changing, so nothing is constant there. Don't fall into that trap. When I take the derivative of this with respect to time, I'm going to get 2x then dx dt plus 2y and dy dt equals 2L, and then the thing I'm looking for, which is the change in the length with respect to time, dl dt. All right? Now I know everything except this. I can find out L by using Pythagoras. 1/4 squared plus 1/4 squared square rooted is going to be radical 2 over 16. Okay, you can check that out for your length. And then when I square root that, sorry, radical 2 over 4 I meant, because I have to take the square root of 16. So you can find that out on a calculator. But now I can plug in everything that I know. 2 times 1/4, that at the snapshot, that's the distance I am from that intersection. Then the change in my x is 45 miles per hour, plus 2 times 1/4 is my y distance, and that's 60 miles per hour, and that equals 2 times L, which is radical 2 over 4, and then the thing that I am looking for, dl dt. Okay? When you do the math, you're going to get 1/2 of 45 is 22.5, and then when I take 2 times 1/4 of 60 is 15, that's plus 30 there, and then that's going to be equal to, cancel a 2, and radical 2 over 2 is 0.707. So when I divide 22, that's 52.5 divided by 0.707 gives me an answer of 74.25 is my change in miles per hour. So the change in that length, the distance between them, dl dt, is 74.25 miles per hour. Okay? This is a much more challenging problem, but it shouldn't be impossible for you guys. What is the angle changing? That's that angle right there, theta. Okay, at what rate is that viewing angle for this driver looking at the for the westbound driver? This driver's approaching westbound, actually from the east, and looking across at this driver and at the intersection ahead. So really it's just asking at what rate is that angle changing. And now you're going to be given any formulas that you don't have to memorize on the board. To do this then, you just set up theta is going to be equal to, well, that's the opposite side and that's the adjacent side. You could work in L, but we've been given these at the beginning of the problem, so I'm going to do tan to the -1 of my y value, opposite, over my adjacent value, y over x. And all we need to do then is do d theta dt, and then do this d dt. So I'm going to take the derivative of this with respect to time. Well, if we look up in the book, good old problem 21, we've been there and we've done that, 1 over 1 plus x squared. So this becomes 1 over 1 plus, and that's my x, so I put in y over x squared. I put in the y over x, so it's, if you look up, the formula I just gave you was 1 over 1 plus x squared. That's my variable, I put it there. Then I take the derivative of the inside, and that's the quotient rule. So it's this times Well, this times the derivative of y is x, then dy dt, minus y, then dx dt, all over x squared. Okay? And then again, like before up here, we just fill in everything that we know, and we do the math. So very carefully, well, that's 1/4 over 1/4 is 1. 1 squared is 1. 1 plus 1 is 2, so this is just 1/2. So that makes it a little bit easier. Then when you do this math, you get, and I've already worked it out, you're going to get 0.25 times 60, then minus 0.25 times 45, and then all over 0.25, whole thing squared. When you do that, you get an answer of 30. Okay, well, what does that 30 mean? Our problem is given to us in miles per hour, so this is radians per hour. Okay, well, we're not really used to dealing with radians per hour. We could divide by 60, and that's going to be equal to 0.5 radians per minute. If I convert that into degrees, it's approximately 30 degrees per minute. And if I divide that by 60, I'm going to get, it's changing at approximately 0.5 degrees per second. And that's a little bit more how we would think of it as on our human scale. But I would take this as a correct answer also. All right? Good luck.